Hello to those of you who might not have had me face-to-face semester one. The intent of this and the other chapters that I will do is to give you a quick summary of what we did in semester one. I regret to inform you that you're probably not ready to go for the kind of work that we do in this class. What you'll find is that this is a proof class, and I need to teach you about proof, what that is, and give you examples so you can do the work that we need to do in the second semester. So here we start in chapter one. In a nutshell, that just means it's a summary. The topic here are objects, names, diagrams. I will talk about the kinds of objects that we study in this class. I will talk about how we name them, and the kinds of diagrams that we draw for them. In the next chapter, we will talk about the all-important concept of inference. And then in chapter 3, we will talk about the concept of proof, and we will give our first proofs. For those of you who are new to the class, do note this, that I've decided to break the material up a little bit differently. The material here that I will cover in 3 chapters was actually covered in 2 chapters by the students who were actually with me at school. But no matter, we'll still cover the same material. All right, so here we go. Get ready for definitions, get ready for names, get ready for diagrams. First of all, point. This is our basic entity in this class. And we will borrow a definition from that great ancient Greek geometer Euclid, about whom I will talk more in the future. He said that a point is that which has no part. So they don't extend in any direction at all, left, right, up, down, forward, back. That means that strictly they are zero-dimensional objects. As for how we name them, we do so with capital letters. And as for how we picture them, we do so with dots. And you see examples in front of you. You see points A, B, C, and D. Do be very careful about how you name points. We do use capital letters, and then we don't use capital letters to name anything in this class other than points. So please be careful about that. If ever I see that you've used one capital letter, a single capital letter, to name an object, I assume that what you have named is a point. All right, so the next kind of object that we need to define is a line. What Euclid said about lines is that they are limitless, breadthless, length. Limitless means, of course, that they go on forever in each of 2 directions. Breadthless means that they extend only, like you see in the diagram below, left, right. They don't also extend, say, up, down. That is, they're one-dimensional objects. Let us add to Euclid's definition that lines are composed of points. That is, a line is just simply a collection of points arranged in a particular way. As for how we name lines, one way that we do that is with lowercase letters, A, B, C, so on. The line that you see below is a line that has been named lowercase a. And once again, be careful about your use of lowercase letters. The only way that we ever use a lowercase letter is to name a line, or sometimes a piece of a line, but always a line-like object. Now, we do have a second way to name lines that actually is more common. We do it with point names. And most often in this class, we name objects by means of point names, points that are on the object. So what you do in this case is you pick a pair of points on the line, and of course that could be done in an infinite number of ways, and you use those 2 points to name the line. So the line that you see below could be called line AB. That's with a capital A and a capital B. Those are point names, points on the line. Or we could simply write the A and the B together with the line symbol on top. And of course, you see that line symbol. It looks very much like a line. Do note that the order of the points is irrelevant in a line name. So we could also call this line BA, or we could put B and A together with the line symbol on top, as you see. Collinear, we say that 2 or more points are collinear when they all lie on a line. And let me make a point here about our diagrams. We assume that what looks like a line is indeed a line. We make very few assumptions about diagrams, about what can be read from the diagram. But here is one of the assumptions that we do make. If an entity in a diagram looks like it's a line, we assume that it's a line. And moreover, we assume that if a point looks like it is on a line, then it is. Likewise, I should have written this, that if a diagram has been drawn in such a way that clearly a point appears not on a line, we say that it is not. So from the diagram, we can say that points A, B, and C are collinear, and we can also say that D does not lie on that line that passes through A, B, and C. Line segment. A line segment is this. It's 2 points on a line and all the points that are in between them. and we call those points the endpoints. So you see a line segment in front of you. It has two endpoints, and then we'll use those in just a moment to name the line segment. Line segments then are, of course, finite objects. Lines themselves are infinite in each of two directions. Line segments are finite. As for how we name lines, we do so by the endpoints. The endpoints, of course, are points, which means that we use capital letters for them. So then the name of a line segment is, we create that by means of a pair of capital letters. We can simply write line segment, for instance, AB if we like, or we can write the A and the B with the line segment symbol on top. And just as with the case of lines, order is irrelevant, so line segment AB is the same as the line segment BA. Now, polygon. When we talk of polygons, we mean a collection of line segments arranged in a particular way. How are they arranged? Well, we make them join at their endpoints, and we make certain that each of those segments that together compose the polygon intersects two others and does so at its endpoints. So look at the picture of a polygon, the diagram of a polygon that I've given you. It is composed of four line segments. Consider one of them, say line segment AB. Notice that it intersects precisely two other line segments. AB intersects BC, and it also intersects AD, and it does so at its endpoints. So AB intersects BC at point B, AB intersects AD at point A. So if we have a collection of line segments like this, we call it a polygon. Side note here, I think you would have known this, but I should say, each of those line segments that together compose a polygon is a side, and moreover, each of those point of intersection of a side, like in the diagram A and B and C and D, those are called vertices. Now, as for how we name a polygon, very much like the second way that we name a line, we do so by point names. And the points that we pick are names of vertices. So for the polygon that you see in front of you, here would be a valid name, ABCD. Notice what we did. We started at A, and then we simply went around clockwise and picked up all the point names as we found them, and so ended up with ABCD. We could have also started at C if we like, and gone around CDAB. We could have started also at D, and then gone around the other direction as well. We could have gone counterclockwise and gone DCBA. Now, of course, there will be invalid names of polygons, and you get an invalid name when you skip a vertex as you travel around. So if we were to go BDAC, well, that is not a proper name of any polygon here, because when we went from B to D, we skipped C if we intended to go clockwise. If we intended to go counterclockwise, we would have skipped A. So you have to pick adjacent vertices, ones next to one another. Now, for rays. Ray is kind of like a hybrid of a line and a segment. To get a ray, you take a point from a line, and then you take all other points that lie on one of the sides of that point. So what you end up with is an object that is, as it were, finite in one direction, infinite in the other. It's a half line, perhaps. So what that means then is, of course, that a ray has an endpoint. It has a single endpoint, unlike a line segment that has two endpoints. So you see a ray pictured in front of you. As for how we name rays, well, when we named lines and we named segments, we said that order didn't matter. In the name of rays, however, order does absolutely matter, because the first name in a ray, the first point name in a ray name, must be the endpoint. So look at the ray that you see in front of you. It's an A with it's a ray with endpoint A that then passes through B and then later passes through C. Valid names of this ray would be A, B, and AC. Notice that that second point was just some other point on the ray that is not the endpoint. Now, of course, there will then be invalid names if order matters. One invalid name would be BA. Notice that that is invalid because ray BA would start at B and then pass through A. That's not what our ray does. CA would also be invalid because ray CA would start at C and then pass through A, and so on. Intersection, a word that I mentioned before, but let's make sure we're clear about what we mean by this. The intersection of two objects, two geometrical objects, is the set of points that lie on both. That is, to put it slightly differently, it's what's common to them. So look at the two lines in my diagram. One line passes through the points A and B and E. The second line passes through the points C and B and D. Notice then that both of those lines have point B on them, that point B is common to them. So we say the intersection of those two lines is point B. Now, at this point, we have to make a distinction. We have to make a distinction of a segment and its length. Now, the segment is the geometrical object, that is a collection of points arranged in a particular kind of way. However, we can also measure that segment. We can give its length. We have seen how we named the line segment. We put the endpoints together with the line segment symbol on top. Sorry about that. So you see that at the top, those are two valid names for the line segment. If, however, we wish to speak of the length of the line segment, we do not put the line segment symbol on top. So you see simply AB with nothing on top. That designates the length of the line segment. Or if you like, you could put the name of the segment followed by a lowercase m. That would be short for measure of line segment, which of course then is its length. And this distinction will be very important for us because these are, let me emphasize, two very different kinds of mathematical objects. The segment itself is a geometrical object that is composed of points. The segment length is, on the other hand, a number, like 3, perhaps with a unit of centimeters or whatever unit you like. For the most part, we don't concern ourselves with units of length in this class, but still it is a number. Now, we have a way in diagrams to indicate that two segments are equal in length. We do that with hash marks. So look at the diagram. You find there a segment AB and a segment CD, and notice that they both have a single hash mark on them. So what then the diagram has said is that the length of AB is equal to the length of CD. Okay, so diagrams can speak to us just as much as mathematical symbolism or English can. And one way that a diagram can speak to us is we can put hash marks on line segments and say thereby that they are equal in length. We can use more than one hash on a line segment, like in the diagram that you now see. This diagram says that segment AB is equal to segment AG. It also says that segment AC is equal to segment AF, and finally it says that segment AD is equal to segment AE. And the reason we have those equal pairs, we know, is because they have the same number of hash marks on them. So for instance, the segment AD has 3 hash marks, and the segment AE also has 3 hash marks, so we have said that they are equal to one another. Be careful about how you understand how you read hash marks. Yes, if two segments have the same number of hash marks, then they do have the same length. However, a different number of hash marks does not mean that the segments necessarily are unequal. So for instance, this diagram does not say that AB and AC are unequal, but it certainly doesn't say that they're equal. So as far as this diagram goes, we just simply don't know whether AB and AC are equal to one another. And let me emphasize here as well that in our diagrams, if we are not told in any way that two segments are equal to one another, either by hash marks or perhaps just by a bit of English, we'll make no assumption about their equality or inequality. Now, we might be able to prove something about that, but we make no assumptions based on that. So we certainly don't say, for instance, that two segments are unequal because they look unequal, or that two segments are equal because they look equal. We just simply never do that. Midpoint. Let us say that we have a line segment, like line segment AB, and let us say that we place a point C in its interior such that the two subparts, the two pieces created, are equal to one another. In such a case, we say that the point that we dropped is a midpoint. So in the diagram that you see, C was placed on segment AB between them so that AC is equal to CB. That means that C is a midpoint. Now, let us talk about angles. We really have, for most of this class, 2 basic kinds of geometrical objects. One of them is a segment and the other is an angle. So let us define angle in related terms. First of all, the definition of angle. An angle is a pair of rays with a common endpoint. It's as simple as that. So look at the diagram below. In this diagram, we have 2 rays. One of them is GF, the other is GH. They share that common endpoint G. So the object that results, composed of those 2 rays with the common endpoint, that is an angle. Each of those rays, we say, is a side of the angle, and the common endpoint is the vertex. Now, as for how we name angles, we have various ways to do this, but the first and primary way to do that is in this way. We begin with the angle symbol, which you see up top, and then we follow that with 3 letters. And up top, I've simply indicated that we have blanks that will be filled in. Now, what must go in the middle position, that is the second of the 3 positions, is that common endpoint, is the vertex. Okay, so if you look at the angle that you see pictured, the vertex is G, so G has to be the middle name and any valid name of this angle. And as for what occurs in first and third position in an angle name, they have to be points on the sides that are not that vertex. So one way to do it, and these are the valid names, is angle FGH. So that's one valid name. G in the middle, it is the vertex, so that is correct. F is a point on one side, that's not the vertex. H is a point on the other side, that's not the vertex, so we can call it FGH. We could also call it HGF if we like, because the order of the first and the third are irrelevant. Now, obviously, there will be invalid ways to name it. So, for instance, look at the name angle GFH. The reason that that cannot be correct, that it cannot correctly name the angle that you see, is that F is not the vertex. And again, the vertex must always come in the middle position. We also sometimes, actually quite often, name angles with numbers, positive integers, that are tucked into, very often in diagrams, tucked into the vertex of that, close to the vertex of that angle. So you see in the diagram a 1 and a 2. It should be clear from the diagram that 1 is another name for angle RZS, that is the angle that's up top, and angle 2 is the name 2 is another name for angle SCT, which is the angle that is on the bottom. Now, we do this when it's possible to do it, when we can place the numbers in a way so that it's clear that the angle that we name, and we do it typically because it's shorter, it's easier. Angle measure. We talked about segment measure a little bit. Let's also now talk about angle measure. And just as before, we had to distinguish a segment from its measure. Here we have to distinguish an angle from its measure. Angle measure is ultimately based upon the concept of degree. And by definition, a degree is 1/360th of a complete revolution of a ray about its endpoint. And what you are to imagine here is this, is that we have a ray anchored at its endpoint, and it's allowed to spin about that endpoint. And we say that if we go 1/360th of a complete revolution around that endpoint, that is precisely 1 degree. And that is our unit of degree, our unit of angle measure. It is the degree. So for instance, here's a picture. Imagine, well, first of all, we have this angle CAB. That, of course, is a valid name, as is BAC of this angle. Imagine that we allow one of the sides of this angle, say ray AB, to rotate with A fixed so that it then coincides with C. If it had to rotate a total of 120 degrees to do this, then we say that that is the measure of the angle. So the measure of the angle CAB is, in this case, 120 degrees. Now, an obvious question will arise. When I said rotate the ray AB so that it coincides with AZ, I imagined, and I suspect that you did as well, that we did a counterclockwise rotation, and that resulted in 120 degrees. Now, of course, we also could have gone clockwise as well, and if the counterclockwise revolution produced 120 degrees, the clockwise would have to produce 240 degrees. Okay, so it is strictly correct that typically every angle has 2 measures. And of course, it should be obvious that those 2 measures will have to sum up to 360 degrees. Now, the obvious question then is this: which of those 2 measures do we choose? We almost always choose the smaller. Indeed, I will tell you in this class that unless you are explicitly told otherwise, we will just choose the smaller of the 2 possible measures with no comment about that. Now, as for how we specify angle measure, there are 2 ways to do this. We can write it out, and when you do, you see an equation like the one that's in the bottom. The way that this would be read is the measure of angle A is 28 degrees. However, we can also report that 28 degree measure in the diagram itself, and the way we typically do that is we tuck the 28 degrees into the vertex or close to the vertex of that angle in such a way that it clearly labels that angle as one that measures 28 degrees. Hash marks. We saw hash marks in the use in our diagrams that contained segments, and we know that those hash marks are able to tell us that segments are equal in length. We have something very much like that for angles as well. Typically what we will do is we will draw a little arc into the interior of the angle centered about its vertex, and then we will place hash marks on that arc. And once again, an equal number of hash marks tell us that the angles are equal. So notice that two of my arcs have a single hash mark on them. So that tells us that angle BAC is equal to angle DAC. Notice as well that we also have two arcs that have a double hash on them, and that tells us that angle BAE is equal to angle DAF. So just as in the case of segments, diagrams can speak to us and they can tell us that angles are equal in measure. But let me warn you here that just as in the case of segments, we never assume that two segments are equal or unequal based merely upon how they look. The same is true for angles as well. We never say that two angles are equal simply because they look equal. We never say that two angles are unequal because they look unequal. A note about measures, and this applies both to segments and to angles as well. Just by the way that we set up measure and what we mean by that, all measures for us are positive, okay? The length of a segment is always some positive quantity. The measure of an angle is always some positive quantity. But we add, of course, in the case of angles, that positive quantity that represents the measure of an angle must lie between 0 and 360. In fact, it must be greater than 0 and less than 360. All right, so a few definitions that concern angle measure. I expect that you're acquainted with these, but let us make sure that you do understand them. First of all, when we say that an angle is acute, we mean that its measure is less than 90 degrees. Of course, we also know that it's greater than 0. So if it lies between 0 and 90, we say that it's acute. We say that an angle is obtuse if its measure is less than 180 and greater than 90. We say that an angle is right when it measures precisely 90 degrees. And finally, a related notion, we say that two lines are perpendicular when they form at least one right angle. And typically the way that we picture a right angle in our diagram is that we tuck a square into its interior with one of its corners at the vertex. So you see, for instance, there on the left-hand side at the bottom, that we have such a square. So we have said that the measure of this angle is 90 degrees. Now, of course, we could also write the 90 into it, but typically we do it with the square. And on the right-hand side, you see a diagram where we have two lines that come together to make a right angle. So we say that those lines are perpendicular to one another. Complementary. Complementary concerns a pair of angles. Notice that you cannot say that one angle is complementary all by itself. Rather, when you say complementary, that you mean that you have two angles. And what you mean specifically is that the sum of those two angles is 90 degrees. And notice that these two angles, they need not share a side. So for instance, if you were to look at the first example of complementary angles on the bottom, that is the 60 and 30 degree angle, they don't share a side. All that's relevant here is that the sum of their measures is 90 degrees, and that does make them complementary. If you look on the right-hand side, however, we see a different sort of situation where we have a pair of angles. I tell you what, I will indicate them on the diagram, and I will give them names. I will call them angles 1 and 2. Clearly, in this case, the sum of angles 1 and 2 is 90 degrees, and yes, they do share a side, but that's not essential. All that's important here is that their sum is 90 degrees, and so we say that they are complementary. Supplementary is a related notion. Once again, like in the case of complementary, supplementary applies to pairs of angles, and we say that two angles are supplementary when their sum is 180 degrees. And once again, those angles need not share a side. They can be arranged however you like, so long as their sum is 180 degrees. We see two examples on the bottom, the 60 degree and the 120 degree angle. Sum is clearly 180, so we say they are supplementary. The second example on the right, there we do have two angles that share a side in common. And let me label them as I did before. I'll call them angles 1 and 2. Clearly, in this case, the sum of angles 1 and 2 is 180 degrees. So again, we say they are supplementary. Straight angle, particularly important kind of angle for us. Some of our first proofs will concern straight angles. We say that a straight angle is one whose two sides form a line. And notice that in this definition, we don't say anything about the measure. of a straight angle. Now, we will say something about that later on, and I suspect you can guess what we will say that the measure is, but in the definition, we say nothing about the measure. Instead, we simply say that an angle is straight when its two sides form a line. Like you see in the picture, we have a ray AB, we have a ray AC. They do form an angle because they have that common endpoint of A. And if we say then that those two rays form a single line, then that means that angle BAC is a straight angle. Angle bisector. Angle bisector is very much like a midpoint, except of course in this case, we concern ourselves with angles instead of segments. And the way that you get an angle bisector is this, is you place a ray in the interior of an angle from its vertex that divides that original angle up into a pair of equal sub-angles. So look at in the diagram at angle ABC. What we've done is we've placed the ray BP in its interior such that the two sub-angles that result, that is angle ABP and angle PBC, they are equal to one another. So that makes a BP a bisector. So do be careful about this. Bisector doesn't mean simply cut into two parts. It means cut into two equal parts. Adjacent angles. We say that two angles are adjacent when they share a side in common and that common side passes through the interior of the angle formed by the non-common sides. Now, I know that seems a bit complex, but actually the idea is really very simple. Look at, in this case, angles BAC and angle CAD, the two angles CAB and CAD. They share a side in common, that is AC, that is a side of both. And notice that that shared side AC passes through the interior of the angle BAD formed by the non-common sides. Another way to think about this is that you have adjacent angles when, yes, you have a common side, and then one angle is, as it were, on one side of that shared side, and the other angle is on the other side of that shared side. Vertical angles, we will make use of these all throughout our class. All throughout the class, we will prove something quite important about them in chapter 3. For now, we will simply have our definition. However, we say that two angles are vertical if their sides form two lines. So look at the diagram that I have. Okay, consider, for instance, angle ABC and angle DBE. The sides of ABC are BA and BC. The sides of DBE are BD and BE. And notice that those sides form two lines. One of the lines is it's the line that passes through A and B and E. The other is the line that passes through C and B and D. So when you have angles arranged in some such way as this, or in this way, you have vertical angles. Notice that there will also be another pair of vertical angles. And tell you what, I will use a double arc in this case to indicate which two angles I mean. We also have the vertical pair ABD and CBE. And let me emphasize this, okay? The way that you get vertical angles is that you intersect a pair of lines, okay? And the two angles that are vertical are the ones that lie opposite one another when you do so. Linear pairs. I can illustrate the concept of a linear pair with that same diagram that we saw before. Here is our definition. Two angles form a linear pair when they are adjacent and their non-common sides form a line. So for instance, look at angles ABD and DBE. They are adjacent angles. There's the common side BD. And notice that their non-common sides, which are the rays BA and BE in this case, form a line. And clearly there are other linear pairs in this diagram as well. So for instance, let us consider, I tell you what, I'll do it like this. Consider angles DBE and angles EBC. They form a linear pair as well. And how do we know this? Well, they do have a common side. That common side is the ray BE. And the non-common sides, that is the rays BD and BC, they form a line. Now, there will be other linear pairs in this diagram as well. There will be 4 total linear pairs, as a matter of fact, but I think 2 is enough. All right, so that's it for the first chapter. There will be other definitions in later chapters, but the definitions that we have seen are the core definitions, and these are the ones that we will use when we start to do our work on inference in chapter 2, and when we start to do our proofs, our first proofs in chapter 3.